Hello everyone. Today we are going to derive the shape functions of a 4-node quadrilateral element by shortcut method. So this is not a conventional method of deriving the shape function, but rather we are going to follow a shortcut method to derive the shape functions of 4-node quadrilateral element. But keep it in mind that this is a method that you can actually use to derive the shape functions for other higher order elements, not just 4-node quadrilateral element. For example, in today's video, we're going to solve for 4-node quadrilateral element, but in future, we can actually do it for higher order elements, for even an 8-node quadrilateral element, 10-node triangular elements. We can actually pull the same trick to derive the shape functions. But before we delve deeper into deriving the shape functions for your 4-node quadrilateral element, what we are going to do is we are going to recapitulate some of the concepts that we learned last class in deriving the shape functions. So we will very quickly recapitulate what we did last class to derive the shape functions of a 4-node quadrilateral element by conventional method. Okay, so there you can see the master element on the right side, and you can see the actual quadrilateral element on the left side. You can see the master element that is denoted by the coordinates epsilon and eta there, and you can see the actual quadrilateral element. It is reckoned by the coordinates x and y. Keep in mind that the actual stresses we have to compute for the quadrilateral element, not for the master element denoted by epsilon and eta. We are using this master element only to come up with the shape functions in a very easy fashion. So it becomes easy for you to derive the strain displacement matrix, and thereby coming up with the finite element formulation for this particular element becomes easy, and that's the reason why you go for isoparametric formulation. Okay, now without further delay, in the conventional method, the first step always is to assume a trial solution. There you can see the star equation that you are seeing, that is the trial solution that you have assumed. Now, you can actually add more number of terms in this trial solution, higher order terms in the trial solution. That will actually lead to higher order elements. So if you are choosing a higher order element, then you will actually be having more number of terms in the trial solution. Okay, the first step is to assume a trial solution. In our case, it is A0 plus A1 epsilon plus A2 eta plus A3 epsilon eta. The second step is to apply the boundary conditions. The boundary conditions are quite straightforward, that you can see at the nodal point 1, the displacement along the x direction, along the horizontal direction is u1, along the vertical direction it is v1, and at nodal point 2, the displacement is u2, v2, so on and so forth. So you apply the 4 boundary conditions, that is the boundary conditions for horizontal displacements, and you get the 4 equations. And you can see there are 4 equations and there are 4 unknowns, A0, A1, A2, A3. All you have to do is just solve the 4 equations for the 4 unknowns, A0, A1, A2, A3. And once you solve the 4 equations for the 4 unknowns, you can substitute the value of A0, A1, A2, A3 in the star equation. You can substitute those values here. Okay, and those values will be in terms of u1, u2, u3, u4. So that's what you have to do when you actually solve the 4 equations. So that's what we did last class, and we were able to solve the 4 equations, substitute the values of A0, A1, A2, A3, and A4, and you were able to take the coefficients of u1 outside, that is n1, and you are able to take the coefficient of u2 outside, that is n2, and the coefficient of u3 outside, that is n3, and the coefficient of u4 outside, and that is n4. So u of epsilon comma eta is equal to, it is of the form n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Similarly, the vertical displacement at any point inside the master element epsilon comma eta can be given as n1 v1 plus n2 v2 plus n3 v3 plus n4 v4. Okay, the first pattern that we are going to see here now is, if you look at this master element at this nodal point 1, you see The nodal point 1 coordinate is minus 1 comma minus 1. So at minus 1 comma minus 1, which means at when epsilon is minus 1 and eta is minus 1, the value of u should be u1. And other values of displacements should not exist. There is no point for other values of displacements to exist at this nodal point, right? The value of the horizontal displacement is u1, okay? So which means that if you substitute minus 1 comma minus 1, in this particular, if you just substitute epsilon is minus 1 and eta as minus 1 here, then what is going to happen is the value of n1 should evaluate to unity. Thereby you get u1, and the value of n2, n3, n4 will all be evaluated to 0. Okay, so only then you will get u as u1. Okay, n1 should become 1 and n2, n3, n4 should become 0 in order to satisfy the boundary conditions, and you have derived these equations by applying the boundary conditions. So obviously it is quite axiomatic that it has to satisfy the boundary conditions. Okay, so at minus 1 comma minus 1, the value of n1 should be 1 and other n2, n3, n4 should all become 0. Okay, to satisfy the boundary conditions, and it will satisfy the boundary condition. If you want, you can just check it through. At minus 1 comma minus 1, n1 is becoming 1 and n2, n3, n4 are all evaluating, becoming 0, and it will become 0 because that's how you have derived. That's how you have derived these shape functions by applying the boundary conditions in the first place. Okay, so this is the first pattern. Similarly, the value of n2 should become 1 at nodal point 2, and the value of n1, n3, n4 should become 0. Similarly, at nodal point 3, the value of n3 should become 1, and other shape functions should become 0. So you know where the story is heading. Now, the second pattern that I want to see is, you see, localize your attention on this particular term. That is, I want you to concentrate on this particular term. Maybe look at this term. Oh my goodness, it's look at this term here. This term. Maybe I can use a different color. This term, right? 1 minus epsilon. What is that term? Well, it is 1 minus epsilon, but if you look very carefully at that term, 1 minus epsilon is an equation of a straight line. Now, what is that line? So, maybe it can occur to you, right? If you look for patterns, it can occur to you that 1 minus epsilon, oh, that's an equation of a line. And what is that line? So, that line is, if you look at this this equation, 1 minus epsilon is equal to 0, then epsilon becomes equal to 1. If you look at that, you see that this is the line. Maybe I can take a scale and I can bring that here and watch it here and tell me what is the equation of this line. I hope the scale is visible, and I can actually draw a line, right? Maybe a thick line should be possible. Yeah, so let me draw a very thick line. Can I use a different color? What is the equation of this line? Okay, the equation of that line is epsilon is not at all changing, so epsilon should be equal to 1. And that would mean epsilon minus 1 should be equal to 0. So that is a pattern. Now, why I'm saying that is a pattern? The reason why I'm saying that is a pattern is because you look here, epsilon is equal to 1, which means epsilon minus 1 is equal to 0, or 1 minus epsilon is equal to 0. Converse is equally true, right? So you see, that pattern is coming. So in our case, it is epsilon minus 1 is equal to 0. If you multiply, hit it by minus 1 on either side, you get 1 minus epsilon is equal to 0. So that is the pattern that I was talking about, which means that you can now say this one is actually the equation of the line to 3, right? So that is equation of the line to 3. So let me write that down. So that is actually going to be the equation of the line to 3. So this is equation of the line, equation of line to 3. Okay. And what about 1 minus eta? In exactly the same manner, I can say what is 1 minus eta or eta minus 1. So you can say, let me bring the scale back again. So you can see eta is equal to 1 at this point here. Okay. So let me draw a very thick line here that you can see. This line is the line at which the equation of that line is eta is equal to 1, or you can say 1 minus eta is equal to 0. Okay, you can also say 1 minus eta is equal to 0. So which means, you see, this is the line that says 1 minus eta is equal to 0. So that is the line of the nodal point 3, 4. Okay, fine. So that is the next pattern. Interesting. So this line is the equation of the line that is crossing the nodal point 3, 4. So now there is a pattern that is coming. Shape function n1, instead of following the conventional method, you can now see that instead of adopting the conventional method, shape function n1 can be written as the product of two equations followed by a constant. Okay, so now a very clear pattern is coming. So now I can say shape function n1, now I can write very nicely here, n1 should be equal to some constant phi1 into equation of the line 2, 3 into equation of the line 3, 4. This is one pattern that is coming. Again, the important point here is, if you look at this pattern, the line equation does not cross the nodal point 1. You see, the red lines are not crossing the nodal point 1. So when you're trying to define the shape function n1, right, when you're trying to write the shape function n1, it is the equation of the two red lines that is not crossing the nodal point 1. So that is another pattern. Okay. Now, shall we try for n2? n2 should be the equation of the line. From following from this pattern, we will try for n2. Okay. n2, let me take a scale. n2 should be the equation of the line. Yeah. 1, 4. Okay, equation of the line 1, 4. Maybe I can use a different color. Maybe the blue will do, I guess. Okay, so the blue color. Okay, a thick one. Let me choose a thick one. Okay, all right, then this one, this blue. Okay, that equation. So what is the equation of that line? The equation of that line is eta is always equal to minus 1. Eta is equal to minus 1. Okay, so I can say eta is equal to minus 1, or I can say 1 plus eta is equal to 0. So that equal to 0. Okay, so the equation of the line is 1 plus eta. So let us see whether 1 plus eta is out there for n2. So for n2, is it 1 eta is equal to minus 1, right? So that means that, okay, 1 plus eta, if you bring it here, 1 plus eta should be equal to 0. Okay, we are trying to find the shape function for n2. So it should be the product of the two lines, the line 1, 4. And what is the equation of the line 1, 4? Well, oh my goodness, I just made a mistake. Please forgive me. So I just made a mistake. That is, the equation of the line 1, 4 is not eta is equal to minus 1, right? The equation of the line 1, 4 is eta keeps changing. You see, epsilon doesn't change. Epsilon is a fixed value. So let me write that once and for all very clearly. So the value of epsilon is equal to minus 1. it's not changing, the blue line, so you get 1 plus epsilon is equal to 0. Okay, so that you can see 1 plus epsilon is here. Okay, good. And the next line should be, well, we are trying to find the shape function n2, right? So the next line should be this line that should not cross the nodal point 2. So we already know what is that equation. It is 1 minus eta is equal to 0. So there you see 1 minus eta is there. Okay, so you can see 1 minus eta is here. Shall we try for one more nodal point? Let us try to find the shape function n3. So what is shape function n3? It should be the equation of the line 1, 4, which is 1 plus epsilon. There you see. And the other line also should not cross nodal point 3. So it should be this line. And what is the equation of this line? Epsilon keeps changing, eta doesn't change. Eta is equal to minus, okay, eta is equal to minus 1. So you can say 1 plus eta is equal to 0. So you see 1 plus eta is here. Okay, the same for n4. Okay, n4 is already this equation of the line 1, 2, in which case it is 1 plus eta, and the line equation that should not cross nodal point 4, which will be this line, in which case it is epsilon is equal to 1. So you can say it is 1 minus epsilon is equal to 0. You can also see that here. So that is it. So now you know how to generalize the equation. The generalized form is, if I want to find n1, it will be some constant into equation of the line that is should not cross the nodal point 1. So that will be equation of the line 2, 3 and 3, 4. Okay, this will be n1. Now, in order to find the constant phi 1, you now use the technique that is at the nodal point 1, at node 1, the value of n1 should become 1. So n1 is equal to 1 into phi 1 into, what is the equation of the line 2, 3? It is 1 minus epsilon. So it is 1 minus, and the value of epsilon is minus 1. So minus into minus plus 1 into equation of the line 3, 4, which is 1 minus eta. And the value of eta is minus 1. So 1 minus into minus plus. So it's plus 1. So that is it. So this surrenders the value of phi 1 as 1 divided by 4. You can pull exactly the same trick for n2. If you want, I can try for n2 also. So for n2, the equation is phi 2 into the equation for n2. It should be the equation of the line 1, 4, in which case it is 1 plus epsilon, and the equation of the line, and the equation of the line 3, 4, which is 1 minus eta, and at the nodal point number 2, the value is 1 minus 1. So n2 should become 1 at 1 minus 1. So the value of epsilon is 1. So that becomes 1 plus 1, 2. And the value of eta is minus 1. So minus of minus becomes plus. So it is 1 plus 1, 2. So this surrenders again the value of phi 2 as 1 by 4. So you see, 1 by 4 is what you have outside the coefficients. Okay. Similarly, you can find for n3 and you can also find for n4. Now, one more question that you may have at the back of your mind, that is, if you watch this shortcut method, one thing that you have to keep in your mind is, maybe now you know that if I want to find the shape function n1, it is the multiplication of the straight lines that cuts across all other nodal points except nodal point number 1. Okay. Now, I can also draw, just out of curiosity, I can also draw a line like this. Okay, like this. So it will be the line 2, 4 multiplied, you may argue, maybe this line 2, 4 multiplied by the line 3, 4 and multiplied by the line 3, 2. Okay, will it work? No, it's not going to work. Why? Because the pattern is you have to come up with the minimum number of equations. So the minimum number of equations in the sense, in order for you to find n1, the minimum number of equations will be it will be the product of two straight lines, which is the nodal point number 3, 4, the equation of the line 3, 4 and the equation of the line 2, 3. So minimum number of equations will be two line equations, equation of the line 2, 3 and 3, 4. Okay, if you are also taking the diagonal, you are inviting one more equation. Okay, so that's also satisfying our condition, but condition that it is also not passing through the nodal point 1 in order for you to find the shape function n1, but the condition here is the minimum number of equations that you have to take. Okay, that is the pattern. Okay, that is the pattern that it follows. So how this method comes is by observing, by looking for the patterns. So there is no authoritative derivation behind it, but there is a postulation that you can, I'm not sure if I'm using the right word, but there is a pattern. I think pattern is the right word. You can see that the shape functions are product of straight lines, and these straight lines are not crossing the particular nodal point, and also you choose minimum number of straight line equations. Okay, now why I'm emphasizing on minimum number of straight line equations, because when you go for higher order elements, right, like a higher 10-noded triangular element, then this can be confusing. So you look for minimum number of straight line patterns, so that enables you to derive the shape functions quickly and efficiently. Hope the explanation is useful. Thank you all for your